Indeed. Happy Pi Day. Everyone knows what Pi Day is?
Happy Pi Day.
314. Last year was 15.
Yeah.
Yeah, no, not this year. Oh well. Okay. Okay, so we're talking about second derivative concavity. So we know that. It's kind of cool. I was thinking about this morning. The function gives us information about points, right? Individual points on the graph. This first derivative gives us information about lines. And the second derivative gives us information about curves. So if you think about it, we're kind of going from point to line to curve. We're gradually getting more refined in our information. So that makes sense. So let's, in fact, I wanted to start then with kind of how we can interpret concavity. So I'm looking at number 84 on page 268. It's a word problem. I know you're excited. Okay. So a company estimates that it will sell N units of a product after spending a certain number of thousands of dollars on advertising. So when is the rate of change of sales increasing and when is it decreasing? I want to jump to that. Oh, I'm reading 94 instead of 84. Yeah. Sorry, let me try again. 84. We're doing 94 also, but we'll get to that. Okay, so a commonly used measure of inflation is the annual rate of change of the producer price index. The government report states the annual rate of change is decreasing. What does this say about the shape? So we have this PPI, producer price index, and it's the rate of change is decreasing. So what does it mean? So the rate of change is decreasing. So here's our rate, right? A rate is a slope, and it's decreasing.
It's going down.
So what is this shape?
Frown.
Yes, so that's in math language called?
Concave down.
Concave down. Right. So that's the answer to that problem. That's all it is. Yes?
Like, one of the things that confuses me about that, right, is like when it says the annual rate of change is decreasing. But couldn't it be that the slope is like the picture you're drawing, the slope is increasing, but the rate of change is decreasing?
Yes.
But couldn't it also be going down?
Yes. So it could
So
be.
like that's kind of the thing is that like.
But you know what is the same?
The words that are used, like I get the picture, like
right.
I understand the graph.
But these two graphs are the same thing. Here the
right.
slope is positive and it's getting smaller, so that's decreasing. Here it's 0 and getting more negative. That's
right.
also
so
decreasing.
So wouldn't the answer be twofold? That that what that tells us is that it's either increasing, but increasing by an ever smaller amount, or it's
right.
actually decreasing and,
right.
and flattening out.
And not flattening out, because in order for this right here to get smaller, that's 0. What's smaller than 0? A negative slope. What's smaller than a shallow negative slope, a steeper negative slope? Right. So it's the same. When they're saying what the shape.
Two totally opposite behaviors that are explained the same way.
But the shape that we're talking about is that. And so which side of that shape you're on is sort of immaterial for the answer to this question.
Okay.
So yes, you're right. I mean, so yeah, the two different sides are very different in terms of what's happening, but the
right,
shape is the same.
Like if you're talking
right.
about the economy,
right?
Like,
but
there's a huge difference. It's either plummeting or flattening out.
But since we're talking about second derivative, we're just talking about curvature.
Okay.
That's all we're talking about here. Yeah. So when we talk about second derivative, it's the rate of change. The rate of change. What am I trying to say? The increase or decrease in the rate of change. So you're taking a slope, not a point. You're taking a slope and letting the slope change. Okay. Okay, so given that, let's look at, and this is a sign chart from, I think this is number 42, if you're in your book. From the same problem section, just one page back. All right, so we're going to do a lot of graphing. 42, we're going to do a lot of graphing next time. Yes?
I hate that I'm asking so many questions. So if we get an equation like, let's say, x squared, right? And so the first derivative of x squared is 2x, and the second derivative is just 2. Because there's no variable and there's no zeros, do we just take the value of the function and assume that it's continuous with that curvature?
So let's look at this. We have x squared. The
Yeah,
derivative
that was
is 2x.
one of the things that was confusing me last night.
And so the second derivative is 2.
Right, so we just assume that it's positive always, which is what it is?
Yeah, it says that the increase in the rate of change is a
right.
constant 2.
Okay.
Yes, and so there's no inflection. So here's the thing. This gives me a point I know goes through 0, 0.
Right.
This gives me, I know, a max min, right? I do a sign chart on that. So I know I've got a min. And then, you know what, we're leading right into one of the applications, so we're just going to do that. I'm going to skip to, so we have this shape here. And what do I have here? If I were going to do a number line, do I have any point at all to put on the number line?
No.
No,
The second derivative?
because it's always
Positive.
positive. So I can write a number line with just, it's just always positive. I know that. Okay, so if there's no variable, it's just always one thing or the other.
Okay, that's why I was wondering if
Okay.
there was no variable, then like,
Correct.
what would you do?
Right. So let's just back up for a minute. Also, if you have something like this, and you want to know what to put on the sign chart, either this is true, or this one is true. Can that ever be true?
No.
No. So there's no point from this one. 2 is not a point on the sign chart. 3, sorry. There we go. I tried to pick different numbers so you know which ones. So 3 is not a point on the sign chart. 2 is because it comes from this factor. And so if you just had, like here, you just end up with just a number 2, then that means there's no variable at all. It's always positive. If I had a derivative, say, of x squared plus 2, 3, do I have a point to put on, is there any point where that's equal to 0?
Whoa.
Right, I'm trying to, for
Zero.
each of these cases,
No, okay.
what is this shape? Parabola, and it's shifted,
3 to the right.
no, up. On the outside, it goes up. So this is shifted up. So will this thing ever go through 0? No, this thing is always positive. So there's, again, no number to put on the sign chart. So sometimes, the only time to get a number on the sign chart is if you have a factor that you can set equal to 0 and get a value, either in the numerator or the denominator. But sometimes you get cases where it's just always positive, or it's just always a constant number, and if it were negative, it'd be always negative. So that's just kind of an aside on sign charts. You must do a sign chart for each and every problem. You cannot know the answer to where is it increasing, decreasing, max, min, where is it concave up, concave down, inflection point. You cannot know without a sign chart. So be prepared to do like 15 every night. Just know you're going to do them. You're going to get really good. All right. So let's come back to this though. This presents one of the concepts that I wanted to talk about today, which is called the second derivative test for local extrema. So this is the very last bit, if you're looking at the notes, it's the very last bit on that page. So here's the thing that's kind of interesting. Here I have a min, right? Do we agree we can only have a min if the derivative goes through 0 or is undefined, right? It has to happen at, in fact, it has to happen at a critical value. But look at this. How do I want to write this? Okay, so let's back up. What if I knew that I had a critical value at some x equals c? And I also know that it's concave up at that point. So what does that mean? I've got this point C. Concave up means the rate of change is increasing. So here, I have a critical value, so let's say I have a slope of 0. If I want the, if I'm concave up, the rate of change is increasing, so this is going to increase, 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 get steeper. Does that make sense? On that side? Now what about on this side? If I need to increase and get to 0, what do I know over here? This has got to be a negative slope, because the only way to increase to 0 is to start negative and then increase to 0. How do I increase to a small negative? And the only way to do that is to increase from a slightly higher negative, a bigger negative. So because it's concave up, is this a max or a min?
It's a min.
It's a min. Can it ever be a max? Not because it's concave up. It can never be a max. Just the way that the slopes have to go in order to match this. So this is what we call the second derivative, put it up here, test for local extrema. So let me give you kind of the whole, so that was kind of the explanation, and now let's write out what you need to do. So the first thing you do, you start with some f of x, you find f prime, and you get all the critical values. So everywhere that the numerator or the denominator is 0, do not do a sign chart. So if you hate sign charts, this one is for you, right? No sign chart. Come down and do the second derivative. We just decided that if it's concave up and you're at a critical point, you know it must be a min, right? There's nowhere else for, this is concave, right? So if it's concave up, then that means you have a min at that critical point. So we're only testing at the critical value. And if it's concave down, what do we have?
Max.
Yeah, it's a max, right? What if it's what if there's what if oh, I'm trying to say. What if you have that? So it's not concave up and it's not concave down. What do you think you know?
Straight line.
You don't know anything. It could. So if this is 0 at that point, then it could be because it's this. It just touches 0. It could be it's that. It could be it's that. You don't really know what's going on at that point, right? Because it could be an inflection point, but you don't know until you do a sign chart. Thank you very much. So if you get this is 0, then this tells you basically just no information on the max min. So if it's concave up, you know it's a min. If it's concave down, you know it's a max. If you don't have positive or negative, you have something 0, then you don't know. So back to sign chart on the first derivative. So why would you want to do this? Sometimes it depends how easy your derivatives are. If you get to a point where this is going to give you a really messy second derivative, don't do this, right? Do the sign chart. So this is a case where depending, whichever one is easier and you prefer to do, that makes sense, but usually there's one or the other that makes the most sense. If the derivative going from first to second is hard, don't do it. I mean, unless you need it for other reasons. So let's look at an example. So here's a question. Is this point 2 f of 2 a local extrema for this function? X cubed minus 6x squared plus 9x plus 1. And that brings up an interesting point. Are you guys able to hear me on the video, or do I need to speak more loudly?
No, you're good.
You can hear okay?
Yeah.
The only problem I'm actually having is that I'm not sure if this happens for everybody else, but it starts to like lag, or it just starts like the connection starts to just fade away. And I'm not sure if that's my stuff
Anybody
or
else having
I don't-
that issue? Okay.
Maybe it's just my laptop. I don't know.
You might try plugging in the laptop, like to
Mm.
power, or
I
no,
don't-
to power, just sometimes, or plugging.
Sometimes it helps.
Yeah, and sometimes too, it helps when you're actually plugged into a network, unfortunately. Some people will suggest that if you're having trouble with, for those of you who do my math lab and have done it in other classes, a lot of times they'll say, if you're having trouble, plug into a network. Yes?
Another thing too is if you're running Wi-Fi in your house or in another area, if you've got a bunch of other things grabbing that Wi-Fi, it's gonna slow you down.
Okay, I just want to make sure most of us speaking loudly enough. Okay, so here's the question. Is this point a local extrema for this? So what's the first thing we need to know? The first thing we need to know is, right, it's got to be a critical point in the first place. If it's not even a critical point, is it possible to have a max min if it's not a critical point? No. Okay, so that's the first thing we have to establish. So the first thing we need to do is the first derivative. This is an easy one. So 3x squared minus 12x plus 9. This is a good reminder that when you're factoring, always factor out common factors first. So I'm going to pull out that 3. X squared minus 4x plus 3. Oh, interesting. I don't know if I meant to do this. Okay. So what are the critical values? 1 and 3. So what's the answer for this?
No.
No. Can't be because it's not even a critical point. You got to start with that. Okay, so let's do another one that's more interesting. So that's part 1 is make sure that it's a critical value. Part 2 is, let's try this one. What about 1 f of 1? Let's look at that one. So same function, we'll just look at another point. So what about this one? Okay, so first we have to establish, is it a critical value?
Yes.
Yes, so critical value. Okay, so if I want to use the second derivative, so I could do a sign chart. We're set up to do that. Or I could do the second derivative test. Is this going to be an easy second derivative to do?
Mhm.
Yes.
Yeah. So our second derivative, 6x minus 12. So do I need to do a sign chart? Yes.
Why would you go back to that when you've already factored out the 3?
Because this means I have to do a product rule.
No, up one. You've already factored out the 3, why wouldn't you just do 2x, 3 times 2x minus
You could.
4?
You could do that.
Okay.
I just have a tendency to just always go, yes. So
Right,
when
but I mean,
you
the
can do either
constant
one.
carries over, so
It
you've already
does.
taken the
And
constant.
and if I do that, but then I'm going to have to factor the 2 out as well when it doesn't matter, either way. That's fine.
Fair enough.
So here, do I need to do a sign test? No. The whole point of this is stick in that, I just want to know the concavity at that point. That's all I want to know. So if I simply plug in that value, I will get the concavity. So if I plug in that, I'm going to get -6. So it is concave down. So do I have a max or a min here?
And then, yeah, max.
Max. So is it a local extrema? Yes, it's a max. Local max, we should clarify that. We'll get to absolute max next time. So when you're answering these questions for the second derivative test for local extrema, the first thing you have to verify is that it is in fact a critical point in the first place. That's okay because you have to do the first derivative in order to come to the second derivative. And then once you're here, you just say, okay, it is a critical value. Let's see what the concavity is at that point.
Wait, I missed something.
Mhm.
How did you find out that it was a local max?
Because this is concave down.
Okay. Oh, yeah, okay, all right, we're good. I'm sorry.
Good? Yeah, it's concave down? Okay. So that's one application of the second derivative. All right, so now let's look at taking a set of information, some points and some first derivative and some second derivative information, see if we can put together a graph. We're going to do a lot more of that next time, but let's just kind of have a taste of it now.
How did you know, right, without actually doing the sign chart, putting in the positive and negatives, whether or not the slope on the function would actually go up? I mean, without testing either of the sign charts, wouldn't it have just been an inflection point where it changed and it wasn't a local max?
No, because if it were an inflection point, the second derivative would be 0. Because the second derivative has a value positive or negative, at that point it's either concave up or concave down. So at that point,
All right,
Yeah.
Roger, all right.
Okay, so let's look at this. Let's look at this information. So I'm going to give you, like we did before, I'm going to give you some points, like an XY table. And this is number 42. So if you want to just look in your book, then you don't even have to copy it down. I'll do it just so it's on the video. -4, -2, 1, 0, 2, 4. So if you want to go ahead and start graphing points, feel free. That's the first thing we always do is graph points. Okay, so we have XY information. Where would we get that from? Where do we get Y values from? Plug it into the function. So this is always f of x data. This is going to be slope data, and this is going to be concavity. So I know that this is going down, and then going up, kind of going flat and going up. And I know that it's kind of like this in terms of shape. That's what it tells both of. So let's see if we can put it all together, because that's kind of where we're going with some of this. All right. -4, -2. Feel free to correct me. It's just as early for me as it is for you. Does that look about right? I think so. Okay, so let's look at what we know. We know it's coming down until I get to x equals -2. So I know it's doing this. And then I know it's going up until it gets to +2. Something like that. And then it keeps, then it flattens out, right? And then it keeps going up. Right, so it goes down and then up. So now let's add some curves to it. So I've kind of dotted it in, but clearly the lines didn't go straight through some of those points, right? So let's look at this. It's concave up until I get to here. So that means kind of a bowl shape. So when I'm coming through, it looks like a bowl until I get to -1, the point at -1. And then what happens? It goes concave down. So now I'm going to start kind of angling this. So if we look at it, when it's bowl-shaped, it's kind of coming under the curve, and now I'm going like that.
But how do you get that sign chart? Oh, it gives it to you.
It just gave, so this
Yeah.
has no function. So this is just an example where you don't even need to know the function if you have this information.
Yeah.
This is what you would generate yourself, yeah. And so now it's concave down, and then it goes concave up again. So we get points from the function, up and down from the first derivative, and then we put in that extra little bit of information, get some curve coming through it. Okay. So again, it's helpful to start with the points, and I kind of like putting these shapes on the sign charts because that kind of gives me a rough idea of what I know to expect over here. Because remember, the sign charts are really just a collapsed, that we've just collapsed the y-axis. These sign charts are exactly the x-axis. So is that okay? All right, so now let's do one last thing. We'll do a word problem business application. This one's called point of diminishing returns, and then we'll be done. Okay, so point of diminishing return. What does that mean to people? Anybody have a sense of what that means?
Is it like a diminishing return where something may have been effective or useful or profitable at one point, but then it just becomes less and less as time goes on?
Yeah, no, is that what everybody kind of has a sense when we say, I've reached the point of diminishing returns? We kind of use that as a phrase, and what it means is, I've been increasing, but now I'm starting to, I might still be increasing, but I'm starting to flatten off. I'm not getting as much bang for my buck anymore. So when I used to have, I was getting a sharp increase, now I'm starting to, kind of flatten off. So even though I'm putting in more effort, I'm getting relatively less out. So what you know about point of diminishing returns is correct. Okay, so let's talk about what it is mathematically. This is the definition in the book. The dollar, here, so we'll say let me just write it out. This is on page 264. The dollar amount at which the rate of sales so the rate of sales, not the sales, but the rate of sales goes from increasing to decreasing. So did the sales go from increasing to decreasing? No, the rate did. So the rate used to be, the rate used to be increasing. In other words, it used to be concave up, right? I'm increasing, the rate's increasing. And now all of a sudden, it's starting to decrease. What does that look like right there? I went from concave up to concave
Inflection
down.
point.
It's an inflection point. So the point of diminishing return is exactly the inflection point. Yeah. So we can find out with which derivative?
Second.
Second derivative. Okay, so let's do an example. Let's look at page 269, number 94. I will read it for those at home. Okay, so a company estimates it will sell N units of a product after spending a certain number of thousands of dollars on advertising. And they give you the formula, the equation that relates those. And then ask, when is the rate of change of sales increasing and when is it decreasing? what is the point of diminishing returns, and what is the maximum rate of change of sales? Okay, so let's write up. So we're basically looking about when the rate is increasing and decreasing. So not the actual function, not the actual sales, but the rate of sales. So let me write up the equation. Okay, it's important to get, it's important to write in this domain as well, because this is not uncommon. A lot of times you will have a model that works for your data, but only within certain values, because maybe outside those values, a different model is required. Yes?
If the domain, because it's a business function, whatever, is set in a certain way with parameters, would that make the ends of the graph local extrema? Because
No.
even though the function goes
Hang tight.
on, the real world application
Yes and no. It doesn't make them local extrema, but it might make them absolute extrema, and we're going to get to that next time. Can you hold that thought?
doesn't. Oh, yeah.
Okay, good. Yes, no, absolutely, we're going there. Just hang on. So when we're looking at this is a fourth degree. Does that excite you guys? I mean, this seems like, would you want to factor this? No.
No.
Would you want to factor a cubic? No. Let's think about what's going to happen, though. So let me just write out a few more things. So X is advertising. Importantly, you need to remember this, advertising in thousands of dollars. So that's an important thing when you're reading through the problem. It's not $15, it's $15,000, and then N is just the number of sales. Okay. Okay, so let's think about what's going to happen. So if we want to know where the rate of change of sales is increasing and decreasing, we know we're looking for a second derivative. So when we do the first derivative, that's going to come down to a third power. So when we do the second derivative, what are we going to come down to? Second. Can we factor quadratics? Yeah. Okay. So first thing we're going to do is do the derivative on this first derivative. So minus, I'm just doing 4 times 0.25 and getting 1, 4 quarters. So negative x cubed plus 39x squared minus 360x plus 0. So that got simple very quickly, and now it's going to simplify further. Minus 3x squared, 78x. So now we need to factor that. Or, what's another way? If you don't want to factor that, if you don't want to take the time or trouble to do that, what's another thing you can do? Always.
Quadratic.
Wow.
Quadratic, right. And I want to know where this is equal to 0. You can always do quadratic formula. That will always work. But let's just do a little practicing. Let's pull out a -3. I like to pull out the negative with it because I much prefer to factor on positive 1x squared. So I'm going to divide 78 by -3. Do I know it's divisible by -3? Do you remember how you know that?
Because 75 is, and then you just add 3.
That would be one way. And the other way is to say 7 plus 8 is 15, when I actually just add the digits, and that's divisible by 3, so the whole number is divisible by 3.
I forgot about that.
I know, isn't that fun? Okay, so I've divided by -3, so it'll be negative. I like the 75 would be 25 plus 1 more, so negative 26. Divide 360 by -3 plus 120. Does anybody see that one right off? What are some factors here? 1 and 120? No. 2 and 60? No. Does anybody see what factors here I can get here? So 2 and 60,
4 and
no,
30.
3 and 4. What's that?
4 and 30.
4 and 30? That's going to give me 34. Let's keep going. 5 and 24, 29. 6 and 20, 6 and 20, there it is. All right, I know it. 6 and 20. So now I need to find critical values. Do I get one from -3? No. So I'm going to get 6 and 20. Except what?
So 6 isn't in the domain.
6 is not even in the domain. So I need to chop this off at 15.